2 was stationary. That's before impact. After impact, one moves in that direction. V1 equals 0.61. The angle we are told is 66 degrees. And the other stone moves off at a velocity v2 at some angle, which we'll call theta. So that is our drawing of what we're trying to model. Initial, final. I'm going to define that direction as positive in y and that direction as positive in x. So what I've got to do is to put 2 equations in 2 directions for initial and 2 equations for 2 directions for the final. So let's look at the initial velocities and see what we get. Well, initial momentum. So initial momentum. What about, let's call this x, we'll call that y. In y, what's initial momentum? How much momentum does it have vertically? 0. In x, momentum is m1 u1. That's the mass of the stone. Both stones have got the same mass. What's the mass of the stone? I'm writing it down. 7 kilograms. So it's 7 times 1.5 kilogram meters per second. So I've resolved the initial momentum horizontally and vertically. What I need to do next is to resolve the final momentum horizontally and vertically. In y, what have we got? Well, I have this mass multiplied by that velocity multiplied by sine cosine, sine of that angle vertically. And it's positive because it's going upwards. So I have that m1 v1 cosine, sine 66 degrees is the momentum vertically. The momentum of this downwards is minus m2 v2 sine theta. Are they both the same mass, the stones? Both 7 kilograms. So I can say that is 7 v1, and I'm going to leave this as sine 66 degrees for the time being, minus 7 v2 sine theta. So that is the final momentum in y. In x, they're both positive, so I have m1 v1 cosine 66 degrees plus m2 v2 cosine theta. So all I've done there, I've said I'm going to resolve the velocities, hence the momentum in that direction, resolve the velocities, hence the momentum in that direction. For the final. Now I'm going to use conservation of linear momentum. conservation of linear momentum. It's conserved in y, it's conserved in x. The initial momentum in y was 0, the final momentum in y is that figure. So in y, initial equals 7v1 sine 66 degrees minus 7v2 sine theta. So, oh, v1, I knew v1, didn't I? No, I don't know v1, sorry. I do. 0.61. That is 0.61. So I can say, therefore, 7v2 sine theta is 7. v1 is this 0.61 multiplied by sine 66 degrees. Cancel the 7 and I get v2 sine theta is 0.61 sine 66 degrees.
John, we can't get the angle without calculation.
You can draw a vector diagram.
No. Because the two masses are equal, so the summation of the two angles should be 90. So the second angle is 24. Therefore, velocity equal.
Go for.
I'm not disagreeing, I'm just saying let's prove it rather than just assuming.
I proved it.
Well, I haven't yet, so give me a chance. I'm pretty slower than you. So in x, I have that 7 times 1.5 is equal to m1, which is 7 times v1, 0.61 times cosine 66 degrees, plus 7 v2 cosine theta. So you can cancel the 7s and you will get, therefore, v2 cosine theta is 0.61 cosine 66 degrees. Oh, sorry, it's 1.5 minus 0.61 cosine 66 degrees. So I've got two components. I've got a v2 cos theta and a v2 sine theta. How can it work? Is that not v2 squared into cos squared theta plus sine squared theta? What's cos squared plus sine squared? 1. So we can say that v2 is the square root of, and this is going back to what we've had last semester, v2 cosine theta squared plus v2 sine theta squared. This is a method, it's not the only method, it's one method to work it. You've got a value for v2 there, use your calculator. You've got a value for v1 there, for the sine theta, the cos theta, stick them in, you'll find v2. Divide one by the other, you'll find the angle. Have a go.